Everyone, thank you for joining. So today I'm going to talk about simplicity in auctions, which is a joint work with Moshe, Babaioff, and Shahar Dobzinski, done while I was a research intern in Microsoft Research. Okay, so before talking about simplicity, let's talk about auctions. So auctions in our context of the talk today is just a protocol between seller and buyers trying to decide how should multiple resources be sold, namely how to allocate the items, who's going to get them, and for what price. And for this audience, it's almost needless to say, auctions are everywhere in the real world, from allocating physical items, competing over computational resources, bandwidth allocation, and even deciding what kind of advertisement we're going to see on our Google search or Bing. And when designing an auction, there are several things to consider, such as the communication between the seller and buyers, computation issues, either by the designer of the auction or the seller and buyers that need to run it. And of course, incentives of the agents running the protocol each have their own goal, and we kind of need to motivate them to play by the rules. And when taking all of those things into consideration, we're sometimes going to get like complicated solutions. Okay, I'm not going to define complicated yet, but we have a sense that we have this desire of auction to be simple, to people want to use it, right? And of course, we're not the first one to think about simple mechanism as a desired property. There's a very long line of works trying to learn simple auctions and their guarantees. Okay, this is far from being a comprehensive list, but some examples which I'm not going to go over. Just wait a couple of seconds for you to observe. Okay, and the first question that we need to ask ourselves is, what is a simple mechanism? Right? Before analyzing one, we actually need to understand what is simple. And the approach taken in many of the papers in this line of work says, we don't really need a definition. We know what a simple auction is, right? We have examples. We think this auction is simple. Let's start to study it. And okay, so I'm just going to go over some example of simple auctions. So one, I think, might be the simplest one, is just bundling all items together, treating them as one big item, and selling it for a fixed price. Okay, so that's, I think, commonly agreed to be a simple auction. That's one example. Another example is selling items separately. We give a price per each item, and the price for a bundle of items is just the sum of prices per item. Okay, and a third auction that we're going to talk about in more details later on is bundle size pricing. In this kind of auctions, we price bundles solely by their size. Okay, we have you can have any 5 items that you want for $10, any 6 items that you want for 11, and so on. And also intuitively a very simple auction. And there are many other examples of what is a simple auction. A different approach.
Now you are, Ron, you are separating from the description of the mechanism to given the mechanism as a class. It's not one mechanism, it's a class of mechanisms each time, is given this class of mechanisms finding, say, the optimal one in that class, which may be different issue than just saying in words what it is.
Agreed. I mean, each one of them defines a class of mechanism, and we can study which is the best one among the simple mechanisms. But
no, that's not, no, my point is not comparing them. I said that there is a different measure of simplicity in the description, and given one such class, in finding in that class the optimal mechanism. That may be a much more difficult problem in one case than in another, despite the fact that both have a very simple description. For example, separate and bundling may require a very different computation, yes?
Yeah.
In terms of the complexity of the computation. Okay.
Yeah, agreed. Okay, but the approach that we're going to take is a bit different, and it was taken by other papers as well, but that's our approach for this. So it's finding a quantitative approach for simplicity. And we're going to define the model that will allow us to compare two different models and saying, this one is more simple than another. And then kind of saying, okay, we're going to give some, being more simple, going to lose some due to simplicity, and kind of having a more quantitative way to measure this property. Okay, so the settings for the rest of the talk is the standard setting of a single seller selling heterogeneous items to a single buyer. The buyer has a private valuation V drawn from some distribution D. We're going to assume the seller is committed to a truthful mechanism M, and that the buyer is risk neutral and aims to receive a bundle S that maximizes her expected utility. Okay, and utility is just the value for the bundle minus its price. So just the standard model. And as I guess most of you already know, every single buyer truthful mechanism can be described as a menu.
Wait, Ron, what do you assume about do you make any assumption about the underlying distribution?
Currently not. I'm gonna elaborate that later on.
So it may be correlated for now.
It may be correlated.
Okay.
Okay, so what is a menu? So a menu is just a list of options presented by the seller to the buyer. So each entry in the menu is a lottery over bundles. Okay, in the example to the right, we have this, for example, these 4 options that says you can buy a lottery ticket, and with 40% you're going to get the computer and telephone, and with 60% you're going to get the painting, and the lottery ticket is going to cost you $5. Okay. And the buyer picks utility maximizing menu entry. Okay, go over all of the options and choose one of them. And we have 2 nice properties. That one, it's never better to lie. Okay, we have incentive comparability property. The buyer just choose whatever maximizes her utility. And second, by having the option of getting nothing and paying nothing, we have the individual rationality property. That is, it's always better to participate in the menu than to participate in the mechanism than just leaving the game. Okay, so under this notion of menu, we can define menu size, which is simply the number of entries in the menu. And intuitively, at this point, we have kind of the definition of simplicity, right? A menu is simple if its size is small. If we have a few entries, it's a simple menu. If we have a lot of entries, it's a complicated menu. Right, so that's one intuition. And as I'm going to show in the next couple of slides, this definition lacks some properties that we're going to expect from simplicity. This definition is going to miss something. Okay, so first example, assume we're selling these 5 items using this mechanism. 32 options, maximal length among all deterministic mechanisms. Okay, mechanisms without lotteries. Is this menu simple or not? So by the definition we just gave, it's a very complicated menu, right? It's maximal length. But there is a short way to describe this menu. So we can just say, this is the selling separately auction that we talked about earlier. We give a price per item. And if we're allowed to choose as many items as we want as the sum, we have a short description, okay? So that's one case that menu size is going to miss some notion of simplicity. Second example, again, 5 items, full length menu, and we have a short description. We can just bundle price bundles solely by those size and have a short description. Okay. So as we just saw, we mentioned earlier, selling separately is widely considered to be simple. Okay. It's almost the canonical example. Yet selling separately has the maximal menu size over all deterministic menus. Okay. It's exponential in size. Okay, and so you can say, okay, we have other ways to describe mechanisms. We don't have to use to describe mechanism. We don't have to use menus. We have, the by many menu that we just saw, the menus that symmetric menus when we ignore names of items and so on. And as we observed, all of such techniques either are not fully expressive. There are truthful mechanisms that cannot be described using these new techniques, or that they suffer from the same problem that selling separately is not simpler than any other deterministic auction, and kind of missing this notion of capturing selling separately is simple. Okay, this is
but that's not true about the additive menu size. Additive menu size is k rather than 2 to the power k. So yeah, it does capture that for separate. I mean, I didn't say for all the examples, but for separate, at least it does.
Right, but you cannot describe all menus. It's not even fully expressive over truthful mechanisms. There are mechanisms that you cannot describe.
But for other things, you're still getting 2 to the power k. It's fine. Mm-hmm. I mean, you are still getting 2 to the power. I mean, it can only reduce the menu size, but it's well defined for any menu.
No, you can describe super additive menus using the by menu mechanism. The by menu menu. You can only describe sub-additive.
Okay, I mean,
yeah, you're missing something. I agree, it's a possible definition, but it's also missing something. Okay, but that brings us to our intuition. We try to rethink what we're going to require from the menu to be simple. And the intuition that leads us is that for a simple menu, it should be possible to easily find a profit maximizing entry in the menu. Okay? And in order to this to be a definition, I need to tell you what find is, among other things that I'm going to tell you. So what find can be, how the seller and buyer can communicate between them and find the profit maximizing entry. So there are standard ways to access valuation. So one of them is just unrestricted communication. The seller and buyer can say whatever they want to each other. So in this case, the buyer can simply send which entry maximizes her utility, right? And in this case, the communication complexity is just log of the menu size. We're gonna have just send the number of the relevant entry. But then we have that selling items separately is again, when we have this definition is equivalent to menu size, and we saw that menu size can capture selling items separately as being simple. So we're back to the same problem. And so the next thing we thought about is using queries, also standard model for accessing valuation. And then we think about value queries and demand queries. Okay, so our definition is going to be that for a simple menu, it should be possible to easily find a profit maximizing entry using standard queries. Okay, and just before I'm going to define it formally, I'm going to stop for a minute just to go over the definition of the query of value and demand queries. So just a quick reminder, value queries asks, given a set S, what's its value? And demand queries are given item prices per item, asks what's the bundle to maximize the profit. Okay? And those are very standard query models. I'm not going to go over these examples, but extensively learned models. Okay, so just a quick example. Assume BAT has a valuation of value 2 to the apples, value 3 for grapes, and value 4 for both apple and grapes. Okay, slightly less than the sum. So for value queries, simply is being asked for a value of a bundle and answer it. And for demand queries, given prices per item, in this case, 1.5, it maps each bundle to its utility and answer the profit maximizing bundle. In this case, the apple and grapes have the utility of 2.5, 4 minus the 1.5 of the price, which is maximal of all. And if the prices are 1 and 1, we have more than one correct answer. In this case, either the grapes or apple and grapes both have utility 2. So one of these bundles is going to return arbitrarily. Okay, only one.
Can I ask something?
Sure.
Is the demand query, as you defined it, is for separate pricing? yes, not for arbitrary pricing. Now, is this an easier problem than for arbitrary prices? Forget about the data. The data for arbitrary pricing, you have to give to the power k data, I mean input. But in terms of computation, the fact that the input is additive over the goods, I mean the prices are additive over the goods, does it make the problem of solving what S maximizes the difference easier? Forget, as I said, forget the size of the input.
Depends on the valuations.
Sorry?
I think it depends on the valuation, and for some classes it's going to be.
I see. For some classes of valuation, for example, if the valuations are additive, of course it's easier. Yes, that's a triviality. But somehow you are tailoring it. You are really tailoring it to saying, well, if the prices are additive, then my problem is solvable trivially. I have a solution. But if not, it's then it's going to be difficult. So, yeah, aren't you really making life easy for separate selling versus everything else? By definition, because I mean, you say demand query knows how to solve that with no cost. Anything else? I don't know.
Yeah, the short answer is yes. I mean, we assume this is an easy question because other people learned it and this is the standard model. And we're going to assume this one is simple because these are the questions the buyer knows how to answer, either computationally, or you can say more arbitrary queries are just too complicated to understand. The buyer is kind of simple-minded and can only answer this kind of demand and value queries.
Look, that's not what you are doing, I hope. So I'm not going to argue, but I don't agree with your answer. But never mind, go on. And unless this is going to be an important point in what you are doing, the demand queries. If they are, I reserve the right to value later. But go on.
Demand queries are important in this work, but it's basically an abstraction, assuming that you know, it's kind of a black box access. You give item prices, and it might be hard to compute the answer. We basically abstract that away and think about the query as one unit, independent of the.
But that's not my point. That you are taking something which, in my view, is arbitrary, but it's good for what you want, and deciding that this has cost one. Okay, and that's something I don't like. But we can argue about this later.
We feel it's natural. We feel it's natural because it's like when you go to the supermarket, you need to pick which items you buy. It's basically the basic problem that you face, right? You have item prices and you need to decide which bundle to buy. So it's essentially the, you know, the most basic problems that you would expect a buyer to be able to answer.
Okay, as I said, I reserve my right but go on.
Sure.
Okay, so we're going to assume demand queries are simple, at least for now. Okay, so back to our definition. So for a simple menu, it's possible to easily find the profit maximizing entry in the menu using the standard queries. Okay, so the implementation complexity of a menu M for a class V of valuations is C if there is an algorithm that, given evaluation V from that class, finds the profit maximizing bundle according to M and use most C queries. Okay, so just a quick example, assume the class is additive valuation and the menu is any kind of menu. So an example for an algorithm, just have one value query per item. You can learn the valuation completely and you can answer any kind of question about the menu. So you have like a trivial upper bound of M queries for additive valuation. So in order for this definition to be complete, some variants, some stuff that we need to specify. So the algorithm can be either deterministic or randomized. In this case, we're going to talk about deterministic implementation complexity or randomized one. The way that we count queries can be either worst case, we're going to assume at most C queries for each valuation from the class, or Bayesian, we're going to assume some distribution over this class and ask for at most C queries in expectation. And the allowed queries are either just value queries, which I think we all agree that are simple, or both demand and value queries that are slightly less simple, but still two very simple query models. Okay, so I think it's time for some questions. It's a good point to start for some questions. This is like the main definition that we're going to use.
So, sorry, but
Ron,
now I can strengthen what I said before. For a general valuation, which doesn't have any special structure, you still have to do 2 to the power k computations of size 2 to the power k, because you have to go over all bundles and to find the optimal. Okay, regardless of whether the description of the pricing is additive or not. Now, it's true that if you have special classes of valuations, then there may be a difference, but then you have to argue why there is really a difference. So again, I don't feel comfortable with this definition. With this oracle, with this black box. Yes, I don't, because this black box is in general a 2 to the power k black box. And the distinction between separate pricing and general pricing is not going to be seen in the computation there.
Okay, but if we're ignoring computational issues, we just think about, is this description simple or not? Okay.
Yeah, but we are taking, okay, I mean, let's not argue about it. Go on. I mean, I think go on.
There'll be another question?
I have another question. Do you assume that your menus are always deterministic?
The definition doesn't require that. We can implement also menus with lotteries. We're only going to discuss deterministic menus today, but the definition calls for lotteries as well.
So then how would you define the demand query?
I mean, I can still ask a demand query. Let's assume my menu is just the option of buying a lottery ticket for getting one bundle for price F and another for price F, with probability F, and it's going to cost $1. So I can implement it using one value query for the first bundle, one value query for the second one, and I can compute what's the expected utility from this entry, right? Even if the menu itself is with a lottery. So the implementation is deterministic. The demand queries are deterministic, but they can implement a menu with lotteries. Is that answer?
No, I'm sorry. It's not a value query. It's a demand query that you need to find. You want to find the optimum. No?
No, I'll give an example now. You have.
Oh, I see. For each menu entry, you say you just make value queries as the number of pure outcomes are.
Yeah, I can always have like a value query per entry and see what's its utility. And if it's
per entry in the menu.
Yeah, and if it has lotteries, lottery over bundles, so per bundle in the menu. If there are several bundles that appear in the same entry, I can still have a value query per each and just compute what's the expected.
So it's not that if you have a lottery, you can ask one value query for the lottery ticket.
No, I'm going to assume deterministic queries.
Okay.
Note that for, say, additive valuations over 2 items, you can just query the value of the first item, the second item, and then no matter what the menu is, you can actually implement it, right? Because you have all the information. So you don't need to ask it per entry in the menu. For additive valuations over m items, it's enough to query m value query.
Yeah, but you do not restrict yourself to additive valuations, if I understand correctly.
Right. So we'll study different classes of valuations.
For additive valuations, is one demand query. That's it. I mean, why m? One. It's one demand query.
No, if you have a menu that is not selling separately, a complicated menu, even if the valuation is additive. No, but how can you solve it using few demands?
I see. You said additive valuate, not additive. Okay, sorry.
Yeah, the additive.
My mistake. Okay, I misunderstood what Moshe was saying. Sorry, my mistake.
Okay, so some remarks, we already mentioned some of them. So for additive bias, the implementation complexity of every menu is at most m. We can just have value query per item. So the implementation complexity depends on the class of valuations, right? For more complicated buyers, we're not necessarily going to have this property. Okay, so just the definition of additive, valuation is additive if we have value per item, and the value for a bundle is the sum of values. We all know that. Okay, second, for deterministic menu, the implementation complexity is at most the menu size. Right? As we said, we can ask one value query per bundle that appears in the menu and compute the utility. Another thing that's important to notice is that the algorithm must always find an exact profit maximizing solution to ensure incentive comparability. Okay, if we're going to have only approximation guarantees or high probability guarantees, the buyers might have an incentive to misreport their valuation to the queries, and we don't want to deal with that. So we're going to assume that the algorithm must always find an exact solution. Okay, and when earlier I say randomized algorithm, it's just going to be randomized, like only going to affect the running time.
Sorry, I'm confused now. I'm sorry. Okay. So if you have a very complex menu of an arbitrary size, again with mixed outcomes, okay, but your valuation is additive. Okay, so you make, I guess M is the number of goods. So you make M value queries to find out what your valuation for each good is. But then you have to go over each menu entry, and you have zillions of those, and compute their value to find the optimum, right?
Yeah, but that's the problem of the seller. We're going to ignore computation.
Not the seller, it's of the buyer. The buyer has to solve his optimization problem. I thought that you are talking about the simplicity of the optimization problem of the buyer. That was your criterion. Okay, no? So it sounds to me like the buyer still has a lot of computation to do.
Okay, so the way I look at it, the seller has a menu.
The mechanism is given. The mechanism is fixed, right? We are now taking a fixed mechanism and asking how complex that mechanism is.
Okay, so I think the right way to think about this is the seller knows the mechanism. The buyer doesn't even care about what the mechanism is. She doesn't know it. Okay, all she knows is that the seller is committed to some menu, and the seller tries to find for her what is the profit maximizing solution.
Okay, whoever, I don't care. Call it the seller, call it some machine. I don't care. Somebody has to make this computation of finding the optimal solution. And if the menu size is huge, then this computation is going to be huge, even though you define, even when the valuation is additive, and you say that the implementation complexity is at most M, which I think.
Sergio, you shouldn't think about computation at all. This is a communication model. We only think about communication. We don't allow arbitrary communication, but only communications through these queries. And we only care about like the number of queries, and computation is free. That's the model.
I see. Okay, you didn't say that until now, or I missed it.
That's the definition of implementation complexity.
We're talking about just query complexity.
It was implicit.
I'm sorry. Look, I'm not a computer science guy, so if you don't tell me things explicitly, I am going to miss them. I'm sorry. So you say that we should look at communication only because computations are free. Is that
we only count?
Okay. Sorry, I mean, I didn't get that.
Sergio, computer scientists don't care about computation. That's the thing.
Yeah, I know. That's a good way to put it, Michal.
Yeah.
Thanks. Okay.
So next things to observe: selling separately and selling as a grand bundle are both can be implemented using a single query. Right? Selling separately, we can implement using a single demand query. Selling as a grand bundle, we can implement using a single value query for the value of the grand bundle and just subtract the price. Right? So each has an implementation complexity, which is one. Okay, almost by definition, they are the simplest menus that exist. Okay, and for the rest of the talk, we're going to see whether or not bundle size pricing is a simple menu under our definition or not. Okay, so that's what we're going to do for the next 30 minutes. Okay, so let's try to learn bundle size pricing for additive valuations. Okay, so for additive values, we already said implementation complexity of every menu is at most n. Okay, so in order to say that bundle size pricing is simple, we need to show that it can be implemented using much fewer queries. Okay, so our first theorem, it can be implemented using polylog many queries, or at least almost implemented. So what do I mean by almost? So it says let M be any bundle size pricing menu, okay, and D any distribution over additive valuations, including with correlations. Then for any epsilon, there is a menu M prime, such that it has almost the same revenue, and M prime has an implementation complexity, which is poly-logarithmic in M. Okay? And this notation of revenue is just the expected revenue for the seller from M when V is sampled from D. Okay, and this is an exponential improvement compared to the trivial upper bound of M value queries. So indeed, bundle size pricing is in some sense simple. Okay. Any questions on that? Okay, so the proof outline is going to be assembled from two parts. So first, we have a list of bundle sizes. We want for at least for one specific bundle size to be able to solve this problem. So for a given k, we want to find a set of size k of highest value, and then we can subtract the price of that the price for that size and get the highest utility for that size. Okay, so that's great. And if we have this algorithm, then the second part should be solving for every size separately, right? But of course, we want a poly-logarithmic implementation complexity, so we can't really go over all of the M possible sizes, and we need to do something extra. So the second part will be to build a shorter menu based on the former menu and the distribution, while keeping most of the revenue. So we're going to round some of the prices, we're going to eliminate some of the sizes, and we're going to get a shorter menu. But turns out that this technique still comes with a bit too long menu. If you want to have a poly-logarithmic implementation complexity, you need to do one extra step, which is showing that for this construction, for each valuation V sample from D, only a small subset of the bundle sizes should be considered. We don't really need to solve for every size separately, but only for some specific sizes. And when I say small, I mean poly-logarithmic, and it's going to be an expectation over D. So for some valuation, we're going to consider, we need to solve for more. Okay, so is the outline clear? Okay, so,
could you explain again what do you mean by the second step? Like the different variations will see the same menu, but for some of them it will be easier to find the one maximizing.
Yeah, exactly.
This is what this is saying?
We're going to build a shorter menu, but it's not going to be short enough. We don't need to think about it as short. But for each valuation, we're only going to need to look at several entries. We only, by using a very few queries, we can eliminate a lot of sizes as irrelevant.
Okay.
Okay, that's going to be.
Okay. Yeah. Thanks.
Okay, so a bit more formally, the first part is showing that for additive valuation, there exists a randomized algorithm that finds a k-optimal set using poly-logarithmic many value and demand queries. Okay, and k-optimal is just a set of size k of maximal value. Okay, and the second part is going to show, we're going to show that there is a bundle size pricing menu M prime that has almost the same revenue, and at most polylog many sizes should be considered in expectation over D. And the set of relevant sizes is determined using a single value query.
So just to make sure you understand, if you were to use only value queries, you would need M for the first theorem I'm talking, right? You need M,
theorem?
but the fact that you are now allowing also to use demand queries, you can get log M or polylog M.
Thank you. So that brings us to the tightness question. Okay. So I made a lot of assumptions, not just demand and value query. I assume the valuation is additive. I assume that the algorithm is randomized, and I assume I'm going to use both demand and value queries, right? And then, do I need all of that in order to get the poly-logarithmic algorithm? So, okay, so first the Sergio question.
So just Ron, maybe before you go into these details, do you know that under these assumptions, do you need these many queries?
Like poly-logarithmic, is it can be implemented in a constant? No, I'm not.
You don't have a lower bound.
We don't have a polylog lower bound. Yeah.
Okay.
We consider it simple.
Okay, and another question, does the problem become easier if you assume independent valuations? If you restrict D to be a product distribution?
What's a product distribution?
Yeah, I'm not sure. I'm not sure if you can get.
Oh, for each.
I'm assuming not.
For additive, yeah.
It's going to be equivalent.
By the way, for k equals m, it's not polylog. It's just one. So, Michal, the answer is cannot be polylog for all k, because for at least one k, namely k equals m, the answer is one.
I assume the question was, for example, if we have a lower bound for k equal m over 2.
Yeah, so probably are talking about k of the order of, I don't know, square root m or something, I don't know, something that is not, not close to the extreme.
Yeah.
Yes.
So we don't have a lower bound.
Okay.
But these are the lower bounds that we do have. So Sergio's question about, do we need both demand and value queries? So the first lower bound says that any randomized algorithm must use m over log m many value queries. So maybe not all m, but almost all m queries. The second assumption was that the algorithm is going to be randomized. So the second lower bound shows that for additive valuations, any deterministic algorithm that finds the best bundle of size k must use square m many demand and value queries. And the last assumption was that the evaluation is additive. And the last lower bound says that for submodular evaluation, any randomized algorithm must use exponential number of demand and value queries.
Those things are, you want to find an exact k optimal or
an exact k optimal? Yeah. Yeah, for the last result,
no, for the second theorem, I'm saying that you must use m over log m value queries.
Yeah.
Oh, you must use, sorry, it's a lower bound. Oh, okay.
It's a lower bound. Yeah. We don't, I'm not sure about the upper bound.
Ron, I'm probably confused, but how does this second theorem, we know that for gross substitutes valuations, you can implement a demand query with polynomially many value queries, right?
Mm-hmm. Yeah. So.
Okay.
So yeah, it's a lower bound which is sublinear.
Yeah, sure. Okay.
Yeah.
Okay.
Yeah. So yeah, for gross substitutes, you can solve it using linear many value queries. Using a quadratic many value queries. Okay. So the result in these slides are kind of ordered in an increased technical difficulty. We're only going to discuss the first two in the talk today, maybe only just the first one.
I'm sorry, how come you can still, even randomized, if you want to find a k optimal set, you must know all the values because maybe the one that you didn't check has a huge value. The one item you didn't check. So how can you do with strictly less than m value queries? I don't understand.
What?
If you are getting an exact solution.
For randomized algorithm?
Yeah.
Sorry for.
You are not exact solution is probability for sure, not with probability 1 minus epsilon for sure. You must know all the values of all goods. Otherwise, you may be missing the one that has the highest value, and then you didn't get the right solution. So it's omega of m. So it's m.
Sergio, he will prove the first result, so you will see. But the randomization is used in order to say that in expectation, the number of queries is small. So the solution is exact, but the running time is in expectation. The number of
expectation.
Think about sorting, right? When you do sorting like or binary search.
So another point, maybe a different point, is that you are allowed to query values of bundles of items. So, for example, your first query might be, what is the value of the full bundle? So, there might be a smarter thing to do than just querying each item separately, right? Because you're allowed to
I see. Bundles. So, value query may be on a bundle, not necessarily on an individual item.
Yes.
I see. Okay. Okay, that may help. Okay, thank you.
So I think that's the main issue, right? Maybe not the expectation.
But for the
Okay.
second lower bound, that value
Okay.
queries can be on bundles.
Okay.
Yeah, because then if you say half of them are this, and then you don't care how it splits. If it's small, you can ignore all of them. You know, if the first half is small and the second half is big, forget the first half. Yes. Yeah.
And these queries are of course adaptive, right? After you learn
everything is
something,
adaptive.
So if it's static, I guess if it's non-adaptive, I guess it's different.
Yeah, if it's not adaptive, I think you can't really get.
Yeah. Okay. Then it goes back to Sergio's question, I guess.
Yeah.
Okay.
Yeah, but the algorithm is. Yeah, we're gonna assume everything is fully adaptive. Okay. Okay, so I think it's time for seeing some algorithmic results. Okay, so we're going to show that for how to find the k, a best bundle of size k using demand and value queries. Okay, so let's observe that for additive valuations, if you put the same price p for all items, it's going to partition the items to items of value larger than p and items of value smaller than p. Right, because we're just going to decide which item is in demand based on specific marginal utility, and we're going to take in the demand every item of value at least p. So we can suggest the following algorithm that uses items as partition pivots. So we choose randomly an item of value t as a pivot. We're going to classify all items as either larger or smaller than p, and we can remove all items that are definitely too small, or keeping all items that are definitely high enough. Going to see just a quick example to describe that. So here's a quick example with 9 items in k equals 3. Okay, so we choose pivot randomly, make a demand price for its price. Okay, we have items, 4 items that are in the demand, 4 items that are not in the demand, and the pivot might be in the demand or not. It's going to have a marginal utility of 0. Okay, and since k equals 3, we know for sure that we don't want to take, and we're never going to take any of the red items, right? Because we're only going to need 3, and the green items are definitely, each one of them is larger than any one of the red ones. So we can rule out all of the 5 small items and continue with the rest 4. So again, we choose a random pivot, making a uniform demand query. Now the demand set is smaller than k. We have only 1 item in the demand and k equals 3. So we definitely want to have all of the items in the demand in the returned set, but we still need to complete it to a size 3. So we're definitely going to take the 2 items, the 2 largest items. We're definitely not going to take the smallest 5 items, and we can iteratively continue till we have a set of exactly size 3. Okay, so that's should converge at some point to the right side, to a set of exactly size k of the largest items. And intuitively at each step, we're going to either rule out half of the remaining item as being too small, or taking half of the remaining items is definitely going to be among the top k. But there is a delicate issue, which is ties. Okay, so assume we just want to find an item of highest value. Okay, just a single item of highest value, and we have a lot of items that has exactly the same value. So now when we choose randomly an item as a pivot, we're probably going to choose one of these items. Okay, and now the demand, the uniform demand query might return all of these items because each one of them has a 0 marginal utility. So they might as well be in the demand. And we're not going to learn almost anything from this kind of query because, okay, so almost all items are in the demand. We might rule out some of the small, we might rule out the small items, and one of the items equal value, but we really didn't make much of a progress, right? In each iteration, we're only going to rule out 1 new item from the equal ones. Okay, so here's a suggestion how to fix it. So at each point, we're going to choose an item as a pivot, and we're going to classify all items as either larger than t, smaller than t, or equal to t, right? And then we can make sure that we're going to have we're going to rule out a linear size, a linear fraction, a constant fraction of the items of each step. Okay. And what I need to show you is how to find all of the items that are equal to T. So I'm not going to show that. I think we don't have the time, but there exists a randomized algorithm that for any additive valuation and the value T finds all item of value exactly T using log squared many value and demand pairs. Okay, so it's a nice algorithm, but I'm not going to have the time to show it. And immediately,
by the way, Ron, you probably are given something about the range of the values.
No,
because otherwise, how do you find? I mean, you first have to find some uniform price that will be there. Otherwise, you can have a huge number of queries until you get to the right range.
Choosing an item as a pivot. By choosing an item, I ask what's its value using a single value query.
Oh, I see. You start
and
with,
then I get some information about the range. Right?
I see. Okay.
Yeah, so I don't need to make any assumption. I kind of learn it using value query.
So that's using a value. So you first use a value, and then you start using the uniform demand.
Yeah. Otherwise, I need assumption on the range, and it's
okay. Yeah. Good answer. Okay.
Okay. So an immediate corollary is that the implementation complexity of finite k-optimal set is log cubed. Right? We have log in expectation. We have log iterations. Where each iteration is implementable using log squared many value and demand pairs. Okay, so that's our upper bound. Any questions on that before moving to the lower bound? Right. Okay, so the lower bound that we're going to show is that using value queries is not enough. Okay, and we have two results on that. One is that any deterministic algorithm that finds an item of highest value, just the single item of highest value, must use n-1 value queries. We can't really save anything. So I'm not going to show the proof for that. And the second result is that using randomized algorithms, finding the highest, finding an item of highest value, going to require at least m over log m many value pairs. Okay, so just a bit more formally, let alg be a randomized algorithm that, given an additive valuation, makes q value queries and return a maximal value item. Okay, one optimal set. With constant positive probability, then the algorithm makes an expectation at least m over log m value pairs. Okay, and the way that we show it is using a reduction to set disjointness. Okay, so for those of you who don't know, set disjointness is a communication complexity problem. All right, we have two players, Alice and Bob, each given a vector from 0, 1 to the m. And they wish to determine is there an index I such that they both agree that its value is 1. Okay, we can think about this as an indicator for subsets from m items. So Alice has some items, Bob has some items, and they try to decide whether or not they have some items in common. Okay, so that's the reason for the name disjointness. Okay, and it's a communication complexity problem. So the way that we measure how good they perform is by asking how many bits they need to exchange in order to get till one of them get to the conclusion whether or not there exists such an index. Okay, and there is a known lower bound for this problem saying that solving disjointment with constant probability requires omega of m many bits of communication. Okay, so how is this problem relevant to our problem? So we're going to do a reduction. So first, let's define our valuation. So for any bundle S, we're going to define the value of S to be the sum of relevant bits in both Alice's vector and Bob's vector. Okay, for example, the value of the second, third, and seventh item is the sum of second, third, and seventh bit in both Alice's and Bob's inputs. Okay, in this case, 0, 0, 1 and 1, 0, 1. So it's 1 plus 2, and the value for the set is 3. Okay. And now we want a lower bound. So assume there exists an algorithm that accesses W using only value queries and finds an item of highest value. Okay, how can Alice and Bob use it in order to solve their problem? So we can notice that the highest value for a single item in W is 2, if and only if there are two indexes, if there is an index such that for both Alice and Bob, the value for this index is 1, right? Otherwise, all values are going to be either 0 or 1. So if Alice and Bob can implement this algorithm, they can just look at the answer, and if the value is 2, then the set are not disjoint. Okay, good. So how can Alice and Bob implement the algorithm? So each one of them is going to implement the algorithm on their own side. And for each query for the value of a bundle S made by the algorithm, Alice will send the sum of the relevant bits to Bob, and Bob will send the sum of the relevant bits to Alice. Okay, so each going to send a number between 0 and m per query. And each query can be implemented using log m bits of communication between both sides. So since we know that any communication protocol that solves this problem uses omega of m bits, we have that the number of queries must be at least m over log m for any algorithm that finds an item with the highest value with constant probability, right? Because each query is implementable using log m bits of communication. Okay, so let's conclude the lower bound. Any questions? Okay, good. So what have we seen today? So first, the first main takeaway is this new definition of implementation complexity, right? This new notion that we think that captures something interesting, basically saying that for a menu to be simple, it requires us to be possible to easily find a profit maximizing entry in the menu using standard queries. Okay, and we discussed what is standard queries and kind of got to the conclusion that the correct querying model allows both demand and value queries. Right? So one reason for that is we want the implementation complexity to capture selling separately and selling as grand bundle being simple, and we can get it using both demand and value queries. And second, as we just saw, value queries cannot really capture even choosing a single item, the best single item as being a simple mechanism. So kind of a sense, kind of having this feeling that value queries alone are not enough. And we saw some parts of the proof that the revenue of any bundle size pricing menu can be approximately obtained by a simple menu, at least for additive bias. And for the problem of finding a k-optimal set, we saw that there is a simple algorithm for additive bias. And we didn't saw what we mentioned that it is complicated for submodular bias. Okay, so what are the next steps? So we have that bundle size pricing is a simple mechanism. So, but what are its guarantees? Is it even interesting the fact that it's simple? So when the value of each item is drawn IID, that's a guarantee of at least 6, because in this case, both selling as grand bundle and selling separately are can be described as bundle size pricing menus. And we have the guarantee that the best of the two has a 6th approximation guarantee. But what can we say about correlated symmetric distribution? Maybe bundle size price, more general bundle size pricing can still have a nice guarantees, at least compared to other deterministic menus. That is an interesting open question. And second, and a bit more general question is, are there any mechanisms with low implementation complexity which are approximately optimal, right? So we have the best of selling as a grand bundle and selling separately as a constant approximation guarantees for additive bias when the value of each item is drawn independently, and it has a constant implementation complexity. Can we do better using logarithmic many queries? Now, is there like a clear trade-off? Can we map, more generally, can we map the Pareto frontier of number of queries relative to the optimal revenue? So I think that is like the most important question that is still open. And I think that's what I had to say today. So thank you.